Hello, in this video I want to review with you our chapter on geometry, so if you're ready, let's get started. To begin, let's remember how we can talk about complementary and supplementary angles. Remember that a complementary pair of angles refer to two angles that share a common vertex, and when you add up their angles, they add up to 90 degrees. They complete each other to form a right angle. Whereas supplementary angles, again, are angles which share a vertex and which add up to 180 degrees. So they supplement each other in order to form a straight angle or a 180 degree line. So if we notice here in the directions, if we're asked to find the value for x, so that's what they ask us to do here. So determine the complementary and supplementary angles in the figures below in order to solve for x. So in the first case, can you figure out on your own, feel free to pause this video, whether or not you're dealing with complementary or supplementary angles? So in A, what did you think? Yep, A is a complementary set of angles, and that is because they are forming a 90 degree angle. That's what this box indicates, remember? And you're adding up two angles which share the same vertex here, and together this angle plus that angle must add up their measurement to 90 degrees. So if you're told that the first angle, that rotation there, is 8 times something, x is just a variable of some measurement, 8 times something plus 5 is that angle, and the other angle is 3 times that same variable x, 3 times something, plus 8. Now you could sit here and guess, what if x is 1, what if x is 2, what if x is 3, but that would take a long time. So instead, if you understand the relationship that complementary angles are two angles in which when you add their measurements up, you should get 90 degrees, then you can simply fill in what you have so far. So let's see if you've already done that. Feel free to pause the video if you haven't and do it yourself. 8x plus 5, when I add that to 3x plus 8, I better get 90. So then it's just a matter of solving this linear equation from algebra for your unknown x by adding like terms. There's no need to distribute anything because it's a plus sign in front. There's no number in front of the parentheses. So I would have 8x plus 3x, well that's 11 copies of x. And then I can take 5 plus 8, which is 13, and the total must equal 90, right? And then from there, we simply isolate. Remember how to solve a linear equation? I know it's algebra, but we can do this. We can undo addition with subtraction, because what you do to one side, you must do to the other side to maintain balance, just like if you ever take a chemistry class. So subtracting 13 from both sides, what do you get? Well, you have 0 on the left, so it's just 11x remaining. And 90 minus 13 is what? That's right, 77. So then can you figure out what x might be just by looking at it or by solving it? Yeah, 11 times what number gives you 77? That would be 7, right? Or divide both sides by 11 to undo multiplication. Same thing. If you do that, you get x equals 77 divided by 11, which is 7. So if a question just asks you to solve for x, you're done. And you can check that by plugging in 7 into the original expressions, 8 times 7 plus 5, 3 times 7 plus 8. And when you do that, you'll get your two angles, which when they add up should equal 90. So you can verify your solution. Okay, so I've done that one with you. Can you try B on your own if you haven't already done one by yourself? Let's see. So in B, this situation is a supplementary situation, right? So we notice that when I add up this angle plus this angle plus this angle, we must add them up and get 180 degrees. And the reason we know that is because at the extremes, we have arrows pointing in opposite directions. They are 180 degrees apart, right? Sometimes you hear someone say, oh, that person did a 180. They're now looking in the opposite direction than they were when they first started. So that's what happens. This line segment is now facing the other direction after the 3 rotations of those angular measures. So what do we know? Well, we know that the first angular rotation, which was 6x minus 10, when it is added to, these are all technically in degrees to be honest there, is being added to the next one, which is 4x plus 6, which is being added to the next one, which is 7x plus 14. And when you add up all 3 of those angular rotations, you should create the 180 degree rotation, turning it into a straight line. Okay, so same thing as last time. In order to solve, we need to first add up all of our like terms. If you haven't already done so, the setup was the hard part, if you will. If you haven't already done so, go ahead and finish the problem yourself. Did you take 6x plus 4x plus 7x, since those are all your like terms? And adding those coefficients, 6 plus 4 is 10, 10 plus 7 is 17. So did you get 17x? I hope so. And then you have a negative 10, you have a positive 6, and you have a positive 14. Negative 10 plus 6 is negative 4, right? And negative 4 plus 14 is positive 10. So far we're looking at, if I remove the degrees just for convenience here, 17x plus 10 must equal 180. Again, solving for x, we would need to isolate the x term by undoing addition with subtraction. Subtracting 10 on both sides, 180 minus 10 is 170 equals 17x. Undoing multiplication with division, or just looking carefully and saying 17 times what number, because x just represents an unknown number. 17 times what number gives me 170. Hopefully we know the answer to that. It's going to be divided by 10 here. So, sorry, 17 goes in 10 times, I should say. So we're going to have the answer of 10 here. So x is 10. 170 divided by 17 is 10. Okay, now that you have x, you answered the question, but what's more important is that x makes sense, right? All of the math that we teach you in our classes isn't just so that you can get a right answer. It's so that you understand and can justify your answer. So can you take that 10, can you put it back into the original expressions and make it make sense? Do all three of those angular measures then add up to 180? If not, you may have made an arithmetic error. Okay, once you reviewed complementary and supplementary angles, head over to the next problem with me. So the next problem is going to ask us to remember polygons, okay? So this has been at the beginning of the unit. Maybe it's been a minute since you've seen this, but let's see if we can remember. It says determine the measure of an interior angle, so that's an important adjective there, of a regular nonagon. So we have another important adjective with the word regular. And the word nonagon is very important. That's actually telling us how many angles are inside of the polygon. It also tells you how many sides there are on the polygon. So if you remember, when we talk about polygons, another way of saying it was they're called n-gons, okay? Where n is the number of interior angles or the number of external sides, line segments that create the polygon. So in this case, the prefix of this n-gon is non, so nonagon. So what did that mean? Do you remember? That's right, n must be 9. So we had different types. We had triangles, we had quadrilaterals, we had pentagons, we had hexagons, we have nonagons, octagons. Those prefixes, when they end in gon, that's really going to tell you the number of sides and also the number of interior angles. So you have to remember, nonagon means 9, so make sure you have a note card or in your notes you have it organized and you know which is which. Okay, once you know that, you could draw the picture, that's one option, to visualize what's going on. You could also notice that it's asking you for the measure of the interior angle. Now, we had a way of figuring out the total sum of those interior angles. Do you remember that? The sum of the interior angles for any polygon or any n-gon. You remember that formula? And it had to do with how many triangles you actually have inside, right? For example, a triangle has 3 angles inside, right? But there's only one triangle. And if you continue up from there to a quadrilateral, like a square, you have 2 triangles inside. So it was 2 triangles. Then if you go up to the next one, which is a pentagon, you're going to end up with 3 triangles inside of a 5-sided polygon. So it's always going to be 2 fewer triangles inside than whatever n is. So the formula was, take 2 away from your n value. That's the number of triangles. Do you remember that a triangle has 180 degrees for the sum of its interior angles? So that's why there are n minus 2 times 180. There are n minus 2. There are 2 fewer triangles than the n value inside of each polygon. Okay, so with that formula in mind, again, you can have that in your notes. Okay, with that in mind, can you answer the question above? Well, first you're going to need to find the sum of the interior angles, and then we'll get to the part about finding each interior angle. So for the sum, we would need to take 9. So n was 9, we said. So take 9 minus 2. If you take 9 minus 2, that's 7. So in this case, that would be 7 times 180. And 7 times 180 gives me 1260, okay? So this is the total sum of all interior angles for a 9-sided polygon. Now, there's one important thing that we have to notice, I should say, and that is that this is a regular nonagon. What did that mean? Yep, that's right. All sides have the same length, and all interior angles are equal in measure. So if one of them is 30 degrees, they're all 30 degrees. If one of them is 60 degrees, they're all 60 degrees. That only happens in the case where it is a regular nonagon. So that makes it really nice. We could then figure out what each interior angle measurement must be because they all have to be the same. So we can do some division to do that part right now. Let's take a look. We would take our 1260, that's the total sum of all the interior angle measurements, divided by what? Well, how many angles are in a nonagon? Inside angles, interior angles. There would be 9, right? So notice I'm not dividing by 7, I'm dividing by 9 because there are 9 separate angles inside of your nonagon. So when I do that, I take 1260 divided by 9, and what did you get? That's right, 140 degrees each. Okay, so we were able to find the answer. That is our final answer, by the way. So get another color. This is the answer. Okay, that's what we were looking for, and that was found by first figuring out what a nonagon meant, secondly figuring out how do you find the sum of the interior angles, thinking it through or memorizing that formula with n minus 2 times 180. Third, once you had the sum, because of that word regular, we were then able to find out the actual interior angle measure of each one by doing simple division. Okay, so once you have your polygons under review, let's head over to our next review question. Let's talk about similar triangles. Now, technically, we could have similar polygons as well, but in this class, we simply focused on triangles. So suppose we're given 2 triangles, and we're told that they are similar. Now, remember, the order is important here. We are told that we have triangle ABC, and we have triangle DEF. Now, what did that mean? Okay, that meant that triangle ABC has 3 points that are connected, forming a triangle, and those points, or those vertices, are called A, B, and C. So we see that here. There's A, there's B, there's C. And they also told me DEF, so notice D, E, and F. They're relatively in the same placement, but what's most important is that their segments are making sense. AB should be similar to DE, okay? What do I mean by similar in this sense? They're going to be multiples of each other. Maybe one is twice as big, maybe one is 3 times as big, maybe one is half as big. We're going to figure that out, but they should be in similar placement, similar relationship. Similarly, BC, this longer piece here, is corresponding to EF because of the placement of where it is in the title, okay? And AC, that was your first and your third letter, is similar in placement or corresponding to DF, and you see that here in the picture. There's AC and there is DF. Okay, so that's what we're talking about. Now, as far as the actual angles inside, while the sides must be proportional in length, the angles must be identical. So if this is 90 degrees, which it appears to be, then if B is 90 degrees, then E is 90 degrees, judging by the placement of the similarity, okay? And similarly, let's say if A was 20 degrees, then D would also be 20 degrees. And if C was 70 degrees, which is not, but I'm making numbers up right now, then F would also have to be 70. They would have to be the same. So one way that we notice that sometimes is we use these tick marks, like the same tick mark there, like those would be the same, and A and D would be the same, something like that. Okay, so once we understand what's going on by similar, now we can answer some questions. It says, could we determine the length of side DF and EF? And remember that by putting that little line segment above DF, it's talking about the actual length or the measurement of that segment DF. Okay, so let's take a look at DF. Well, DF is actually what we're calling Y in this problem, isn't it? So we want to find out what that equals. And they're also asking us to find EF. Where is EF? Well, that would be X in this problem. So we're really solving for X and Y. And how could we do such a thing? Well, we know they were very kind. They gave us the exact measurements of A to B, of B to C, and of A to C. And they also gave us the measurement from D to E. So could we then find the missing 2 sides? Well, yes, of course we could, by remembering that because these are proportional, these sides are proportional because of the similarity, we are then able to find the answers by creating a proportion problem, setting one ratio equal to another. So sometimes the way we do this, if I called this like the bigger triangle and this the smaller triangle, or in other words, triangle ABC, and this was triangle DEF, okay? What I can do is I can say, okay, how does the big relate to the small? So when I'm creating my proportion problem, that's one way to do it, right? So for the big triangle, I'm going to look at, let's say, A to B first. Let's look at that side first. So A to B, that would be 6, right? So when I do A to B, that's 6. Now, for the small triangle, where is that located? That would be D to E, wouldn't it? That would be 4, okay? Now for the big triangle, let's say I wanted to solve for X first. Well, I know that for the small triangle, that would be X, but for the big triangle, where would that be? Well, that's right, that would be 7, right? That would be B to C. because B to C and E to F are corresponding. So we can set those equal that way, and then we can simply cross multiply. Now this is a skill, in fact, this is one of the reasons why sometimes nursing students have to take this class, because when you are trying to find out how to scale something to size, whether it's you're talking in this case about measurements of a similar triangle, or if you're talking about dosages, right, for prescription drugs that a doctor is prescribing, you would do the same thing. You would set up your proportion problem for the larger patient, the smaller patient. If I give the larger patient, 200 milligrams of a drug, how much do I give the smaller patient for that particular drug? And you could do the same thing, set up a nice proportion problem and cross multiply. So this is a very important math skill that you need for many, many things in life, even if you're just baking and you're trying to go from doubling recipe to making it half as big. Okay, so when we're talking about cross multiplying, remember that means 6 times x is 6x, and 7 times 4 is 28. So in this situation, make sure I had that right. Yep. All right, we're going to get x is equal to 28 over 6. Now, of course, you can reduce that and get 14 over 3. And for a math question, that's usually what we want. But if you were talking about baking, or if you were talking about medicine, you were probably going to get a decimal, or maybe write this as a mixed number, like 3 goes into 14 how many times, and then have your numerator be your remainder of your fraction. Okay, so 14/3 is fine for a math context. So we're going to put 14 over 3 is our length there. And then similarly, if you do the same thing for y, go ahead and pause the video and try it yourself, what do you get? So when you do the same thing for y, well, again, you could have done a ratio problem, big to small. So in this case, you're looking for df. So what you want to make sure you do, though, is use what you have. Notice we did 6 and 7. We had those pieces of information last time. In this case, we're going to use 6 and 8, right? So we're still going to use the 6 because for the small triangle, we know that the corresponding measurement is 4. But for the missing piece this time of y, we would use the corresponding 8 from the big. Okay, so we'd use our y. And when I cross multiply there, I would be getting 6y equals 32, or y equals 32 over 6. And again, 32 over 6 could simplify to 16 over 3 if you're leaving your answer as a improper fraction. Otherwise, you could divide 3 into 16 and get a decimal or get a mixed number. So now we have our answer 16 over 3. Whatever the units are as well, make sure you put your units there for a real life situation. Again, very important skill. Can you set up a proportion problem? Can you cross multiply and verify or find what the new number should be, the missing value should be based on the relationship of proportionality? All right, let's head over to our next example if you're ready. Another geometry question here involves perimeter and area for a quadrilateral. Now, technically, I could have picked any of the closed figures that we've studied in this unit, but I wanted to pick one that might be a little bit uncomfortable for us. So this quadrilateral is a polygon, a closed figure again, with 4 sides and 4 interior angles. And it's kind of unique. It's not necessarily a square, right? It's not a rectangle. But in this case, we have 2 pairs of parallel sides. We would say that the top and the bottom are what we call parallel. We use those double arrows for parallel, right? But we notice that we have those 2 that are parallel, but then the other sides are not parallel. So we have that 1 pair of parallel sides, and that's it. So we had a name for this. Do you remember what it was called? In America, we call this a trapezoid. And if you studied in the British curriculum, maybe in another country, you might have heard trapezium. Same thing, okay? So we're talking about a trapezoid where you have that 1 pair of parallel sides, not 2. Again, the meaning for that would be if you were to extend the pairs out forever, they would never touch if you tried to connect them. Whereas if you were to extend this side here with 6-inch sides, they would eventually touch. So they're not parallel, okay? So with that in mind, do you remember how to find perimeter for any closed figure? Yep, perimeter should be pretty straightforward. To find the perimeter for any closed figure, you would simply add up all the lengths. So you have, let's call this like base 1, B1, and base 2. Let's call this like slant 1 and slant 2. Okay, now I call it slant, I don't call it H, right? H represents height, a vertical altitude from the top to the bottom. So that 4 inches would actually be your H. So make sure you understand the difference. So if we're finding the perimeter here, Perimeter would just be add up all of the external sides, right? So for example, if you had a piece of your house, and maybe this is actually the ground level, and you're putting baseboards around a room that is the shape of a trapezoid, what you would do is add 6 plus 11 plus 6 plus 13, and that would give you the number of inches of baseboard. More likely you'd be measuring in feet, but that's the idea here. So that's what we're going to do here. We're going to take slanted side 1 plus base 2 plus slanted side 2 plus base 1. Again, you could write that in any order. Addition is what we call commutative. The order doesn't matter as long as you add them all together. So this would become 6 inches plus 11 inches plus 6 inches plus 13 inches. And when you add all of those guys up, what do you get? That's right, you should be getting 36 inches, okay? So 36 inches is the perimeter for this particular quadrilateral, which we happen to know is a trapezoid. Now, did you need to know it was a trapezoid to get the perimeter right? No. But to get the area correct, you betcha. So let's talk about area for a trapezoid. How do we find the area of a trapezoid? Well, there's a couple of ways. One is you could divide this up into different triangles, right? You could say, for example, I have a triangle here, I have a triangle there, and then I have a rectangle inside. You can get the areas for the 3 pieces and go from there. Alternatively, oh, well, I just lost a lot, but it's okay. You have it in your notes. Alternatively, what you could have done is you could have said, well, I noticed that I have the height here. There's my height h, okay? And I notice that I want to recognize that this could be 2 triangles, actually. So if I take away just this guy here, okay? I could actually notice that, hey, I have 2 triangles. There's one area of one triangle. And how would I find that? Do you remember how to find the area of a triangle? It's half the base times the height. So you would take 1/2 the base, which in this case would be 11 inches, times the height. Again, height is altitude. It's not going to be the slant height, so that would be 4 inches. And you would end up getting 44 times half, which is 22. Inches times inches is square inches. That would be the area of the first triangle, okay? And then you don't have to find the area of the second triangle. How would you find that area of the second triangle? Same thing, 1/2 the base, which is in this case 13 inches, times its height, which again is 4 inches. Height is from the ground to the top, not the slant height. In that case, you're going to end up getting half of 4, which is 2, and 2 times 13 is 26. So 26 square inches. So once you have the area of each of those triangles, you could have added them together to get your answer. So the total area would be what? 22 plus 26, or 48 square inches. That's our answer just by thinking it through. So if you forgot the formula for a trapezoid, you could still get this answer right carefully. But if you remember the formula for a trapezoid, it should have been, and you can see why in a second, 1/2 the sum of the bases, base 1 plus base 2, times the height. Okay, so where did that come from? Well, notice here we did half base height. So this was like your base 1. And then here we did half base height. This was your base 2. So we ended up doing that twice. Isn't that the same thing as if you had distributed here? Half base 1 times height, half base 2 times height added together. It's the same thing. So your shortcut would have been to take 13 plus 11, multiply by half and the height. And if you do that, you would get your total area of 48. So check it out. Make sure you're comfortable with both ways, because sometimes you're going to forget a formula and you need to be able to figure out how to get the area. Okay, so again, it doesn't have to be a trapezoid, but you need to feel comfortable with any of the polygons that we discussed, finding the areas. Okay, when you're ready, let's head to our next example. Can you find, speaking of different types of shapes, can you find the area of the shaded region in the figure below? Okay, now what we've done here is we actually have 2 figures, okay? So the first figure we have is a circle, and this circle has a certain, what we call radius, right? Now, you might be thinking, I can't find the area of the circle. I don't know the radius. Well, not quite, because when a circle is what we call inscribed inside of a square, and the reason I know that is because it has 4 points on the circle that are actually touching the square. That's called an inscribed circle inside of a square. That would mean that if we know the side of one of the sides of the squares, which we do, if we know one of the sides of the square, I should say, that is 10, right? So that would tell me then I know the radius, because I know the diameter of my circle, don't I? if the side, so you think about a square for a second, those are 90 degrees. You have side, you have side, you have side, you have side. Do you remember how to find the area of a square? Yeah, it's going to be side times side, which is side squared, okay? So we know that, okay? So in this case, we could find the area of this square pretty easily. In this case, it would be 10 times 10, or 100 units squared. So whatever your unit is, it's squared. So 100 square units. That would be the area of the square. But we're asked to find the area of the shaded region. Now the square is going to have more area to cover than the shaded region. In fact, the shaded region shouldn't have very much at all. It doesn't include the entire circle, and it doesn't include those two pieces that are not shaded of the square. So what do I need to do now is figure out how would I find the area of a circle. We had a formula for that, and again, we talked about why that is in our previous video, and it was the number pi, that irrational famous constant that you get anytime you take a circumference of a circle and divide by its diameter. You get pi, approximately 3.14. If you take pi and you multiply it by the radius of the circle times itself, or the radius squared, okay, so radius squared times pi, you get the area of a circle. Now again, do we know the radius of this circle? Well, yes. If we know that the side of the square is 10, what is the radius of my circle? Well, it has to be half the diameter. And what is the diameter of the circle? 10. So the radius must be 5 units. So now we can find the area of the circle. Pi times 5 units squared is going to be 5 times 5 is 25. And 25 times pi would be our answer. Usually we'll say 25 pi, not pi 25. So 25 pi, and this is again in square units, whatever the units are. This would be our area of our circle. So area of circle. Okay, so now we have the area of the square and we have the area of the circle. If I was just asking you to find the area of all 4 of these pieces that are outside, right, all 4 of these, then what would you have done? You would take the area of the square and subtract the area of the circle, right? So we can think that way for a moment. I'll just erase that for a moment here so we don't get confused further. So if I wanted the area of those outside pieces, I would take the area of the square minus the area of the circle, and that would give me this plus this plus this plus this, right? That would give me all 4 of those corners that are not part of the circle. So let's do that. We'd have 100 units minus 25 pi. So that would be the answer for when you add up all 4 of those quadrants together, those corner pieces, if you will. But since they only want 2 of them, and there are 4 of them, what part of that answer do we want? 2 out of the 4, or 1 out of 2? So we want half of that. So for the area of the shaded region, we would be saying, I want half of that answer, 100 minus 25 pi. So you could say, that's my answer. 1/2 times parentheses, 100 minus 25 pi in parentheses. And this is again in square units or units squared. But on the other hand, I should say, not on the contrary, on the other hand, a lot of times we would distribute this answer to make it easier on the reader. So 1/2 times 100 is 50 minus 25 pi over 2. And that would just be a little bit cleaner to look at as a reader. Or negative 25 pi over 2 plus 50 means the same thing. And again, these are in square units, whatever the units are. Maybe square feet, square inches, square yards, square centimeters, we don't know. But again, what we had to do first is recognize the relationship between the circle and the square, because the circle was inscribed inside of the square. That gave us the radius, even though we didn't think we had it at first. Then we can find the area of the square, the area of the circle, and then separate and figure out exactly what part of that answer we are required to have based on the shading. I hope that makes sense. If you have any questions, you know you can always ask. All right, let's head over to our next problem when you're ready. It says, can you use your knowledge of right triangles to find the length of this ladder? Okay, so this is very popular. If you ever walk by a construction site, you will see this. Or sometimes if you walk by people's homes in their neighborhood, they'll have a ladder that's resting on one of the walls. And so that's what we see here. We have a ladder that's resting on the wall of a building, and we are told a couple of pieces of information. One thing we're told is that from the ground to the top of the ladder, that length is 20 feet. In other words, that would be called our height. Okay, that's our height. We're also told that from the base of the ladder on the ground to the actual beginning of the building, that distance on the ground is 5 feet. So that could be like our B, our base. Okay, so we have one part is 5, another part is 20. Now, one thing that's implied, they haven't told me, is that this building is not leaning over, right? Hopefully, if it's a structurally sound building, this is at 90-degree angle. Now, that has to happen for this problem to work the way we're going to do it, okay? We have to know this is a right angle. If it's not, we can't use what we call the Pythagorean theorem. Now, if you are curious, if you ever decide to continue in your math journey and take a course called trigonometry, there are ways to answer questions about triangles that are not right triangles, but you still want to find the missing side. Law of sines, law of cosines, you'll study that in trigonometry. But to use the special Pythagorean theorem relationship, this is required, that we have a right triangle. Okay, so what did we remember from a right triangle? Remember, if we had a right triangle called A, B, C, where C was the longest side, the side across from your 90-degree right angle, what was that relationship? That's right, A squared plus B squared must equal the hypotenuse, or the longest side, C squared. With that information in mind, can you answer this question? Go ahead and pause the video if you haven't already done so and try it yourself. So what did you do here? Well, hopefully you noticed that one of the sides could be called 5, the other side could be called 20, and the unknown side, you could call it C, so I'll call it C here. Okay, so when you square 5, you got 25, I hope. And when you squared 20, 20 times 20, did you get 400? Good. And when you added 25 and 400, did you get 425? You got to do that step before you do any square rooting. Sometimes students want to square root right away. So once you have 425 equals C squared, notice that 425 is not the answer, right? That would be way too big, right? In fact, we have to undo the squaring operation by using the square root. It's reciprocal inverse property. They have an inverse relationship, I should say. So if I do that, we would end up with the square root of 425 to undo the squaring, and that leaves me with just C, because what you're saying is C times itself gives me 425. We need to figure out what C would be. And when you do this, you could leave that as your exact answer, but if it simplifies, most math textbooks or math homework websites or a test is going to require you to simplify. So do you notice here that you could actually simplify 425 because this is actually 25 times 17, and 25 is really 5 times 5. So if you notice, that's really 25 times 17, and 25 is really 5 times 5. Then what you could write instead is you could take out the pair of the 5s. This is your algebra that you might be forgetting, right? If you take out your 5s, you get a 5 times the square root of 17. This would be your exact answer for C. If you instead put it in a calculator, the square root of 425 and hit enter, or 5 times the square root of 17 and hit enter, you should be getting approximately 20.62 units for C. So again, this could be in feet, this could be in inches, it could be in any measurement length. Okay. Keep in mind also from algebra, we would normally do a plus or minus square root because technically you could have a negative number times itself and produce a positive. But when you're talking about a word problem, you can't have a negative measurement for length. And that's why we ignored the negative part here. Okay. All right, when you're ready, if you think you got the Pythagorean theorem down, let's go to question 7 in my review here. Another application question. If the cost of flooring is $3.49 per square foot, and this price includes installation, that's a good deal, find the cost of this project for a kitchen that is 12, remember this apostrophe means feet, 12 feet by 14 feet. Okay, so 12 by 14. All right, so what do we have here? Well, we have a situation where you have 12 by 14, so maybe that's the 14 side, and maybe this is the 12 side, depending on how you draw your rectangular shape. Okay, so maybe this is 12 feet, and this is 14 feet. Just drawing a sketch of a rectangle, okay? Because your room, it's described to be a rectangle. When it says something by something, that's a length times a width, that's implied to be a rectangle. So because of that, you know how to find your area of a rectangle, right? Area of a rectangle is always equal to what? That's right, area equals length times width, or base times height means the same thing. So you know that the area, in order to cover this room, this kitchen with flooring, you would need to first figure out the square footage and then multiply by the price per square foot. And making sure that if you measure in square feet, that you actually purchase in square feet. Otherwise, you're making conversions, so pay close attention to that. So if I do that, I would have 12 feet. And again, you could write 14 first. In this case, it really doesn't matter because the multiplication order doesn't matter. 12 feet times 14 feet in order to get your answer here. And when you do that, you get 168 square feet as your total dimensions for the area. Okay, so you need to cover 168 square feet. Now, you might actually, if you're doing a real life project like this, you're probably going to buy sometimes 10% extra, right? You don't want to get exactly that amount because you might need to make some adjustments, and sometimes you just like to have extra. So I'm just doing the problem right now based on the idea, which is not quite right, that you would buy exactly what the measurement is. So if you took 168 square feet is what I need, and they're charging $3.49 per square foot, then the total price would be what? Yeah, 168 square feet times the price per square foot, which is $3.49 per square foot for every 1 square foot. And what's beautiful about that, if you look at it again, you're multiplying these conversion factors just like you do in a chemistry class or in a nursing class with dosages. You notice that your units of square feet cancel and you're left in dollars, which is what we wanted here. So 168 times $3.49 does give you your answer of your total price of $586.32. So that's a very affordable kitchen flooring job. So hopefully you could find something that cheap, but maybe not. Okay, so you might have to do it yourself. Okay, so again, all we need to do here is notice what the square footage was by finding the formula for area, and then multiply by the price of per square foot. Again, if there were different measurements used, one in yards and one in feet, you would need to make that conversion either at the beginning when it's easier or at the end when it's in square footage. All right, if you think you have that down, let's head over to our next example. So for our last example here, we want to review how to find the volume of three-dimensional figures. So in this situation, I've given you 2 examples, but remember there were other ones that we studied in this module, so be sure to know which one is which in your notes. So in the first case, it looks like we have what we call a rectangular solid. Okay, so you can look in your notes for a rectangular solid. And for a rectangular solid, we talked about, there's no E at the end, for a rectangular solid, we talked about the idea that you could find the volume of a rectangular solid by noticing that you would take your length times your width times your height, right? So for the volume, it's just length times width times height. But the reasoning for that was more important because you're going to forget these formulas. The reasoning was you take the area of your base and then you multiply by the height, and that fills up your volume. The area of this base would have been a rectangular base. That would have been 10 times 3, or 30 square inches. And then I'd multiply by the height, which is 4, and I get my answer of 120 inches cubed. So I want you to understand why you're doing what you're doing. It's the area of the base times the height. So sometimes it's written as big B for area of the base times little h. That was also the way we found the volume of this rectangular solid. But this base is a rectangle, that's why its base area is length times width. So in this case, we would have 10 inches times 3 inches. Oop, that got messy real fast. Gifty, right? There we go. Nope, still. Come on, eraser, you want to go. There we go. Gotta pick the right tool. Okay, so we have 10 inches. Ooh, my computer got grumpy with me. One moment. I'm sure you all can relate to your computers getting mad if you go too fast. Let's see. Well, doesn't want to play nicely. Let's give it a moment. But the basic idea here as it's thinking is you want to take your 10 inches times your 3 inches times your 4 inches, and you should be getting your answer of 120 cubic inches. Okay, so it looks really ugly, but that is what I'm trying to write. Now, as it's thinking, let's head over to our next example here on the slide. We have what we call a right circular cone. And the reason it's a right circular cone is because notice that this cone is not tipped over, so we have a right angle from the top of the cone to the base of the cone. So that is why it's called a right circular cone. There we go, now the computer's less grumpy. For this I got angry again. For this right circular cone, what we'd want to do is find, again, for the volume, the area of the base times the height. So how would I do such a thing? How would I do such a thing? Oh, goodness. Well, what we'd want to do is we want to take the volume is the area of the base times the height. We want to take the area of that base. What kind of base is this? This is a circular base. So if we try to do that, take the area of a circular base, we would get pi r squared. Can you see what r is in this example? It's 20 centimeters. So can you find, go ahead and pause the video while my computer thinks. Can you go ahead and find the area of this circular base? That's right, it would be pi times 20 times 20. In other words, you should be getting 400 pi as the area of your circular base. And then what do you do after you have the area of your base in order to find the volume here? Well, you'd multiply by the height, which is 24. But there's one caveat. Let's see if we can remember how to do that. Oops. Okay, I think maybe we'll play with me. So if we try to find the volume here, what we're going to have is 1/3 times that area of that base times that height. And why does it have to be 1/3? Because technically, remember in our video, if you have a right circular cylinder, you can fit how many cones inside? 3. So this is one of the 3 cones you can fit inside of a right circular cylinder. And what I mean by right circular cylinder was something like this. Okay. So now what we've noticed is this is one of those cones, and there's 3 that fit in there. So what we're saying is we need to take 1/3 of that volume. So 1/3 of pi r squared. Why? Because the area of your base is the area of a circle, isn't it? It doesn't quite look like a circle in this picture, but it is a circle. So the area of that circle, pi r squared, times the height. So when I do that, I get 1/3 pi. The radius is 20 centimeters. I have to square that and multiply by my height of 24 centimeters. Okay, so that's a lot prettier than it was a second ago. You're welcome. So when we do that, we get 20 times 20, which is 400. 400 times 24. And when you do that and multiply by 1/3, the total you should be getting is 3,200 next to a pi. So technically, the volume should be 3,200 pi, and this was in centimeters, so we'd say centimeters cubed or cubic centimeters. You'll hear that, by the way, quite a bit if you ever do go into the medical profession, because cubic centimeters is a very common way of talking about medication that is liquid, typically. All right, so that would be your volume for this right circular cone, And again, if you wanted to find the approximation, put it in your calculator, you should be getting roughly, I'll put it over here, 10,053.096 approximately. That would be your rough estimate when you round here. Okay, so in this video, minus the last part, sorry about that, we have now discussed all of the different types of problems that were found in the geometry module. So if you have any questions when you're working them out yourself, please feel free to reach out to me and get clarification. Because you know, as always, math is not a spectator sport. I'll see you next time. Happy practicing.